Hi, it's Jan Beta, and if you're following my channel for a while, you might know that my favorite home computer of all times is the Commodore 64, for mostly nostalgic reasons, because this was the machine I first had as a kid, and I still love using it, playing games on it, and doing all kinds of mods to it, as you've probably seen on my channel. However, the system has some significant problems, one of which being these power bricks, which quickly turn into kind of C64 killers if they fail. And there's a couple of workarounds for that. There's a couple of aftermarket power supplies nowadays. I built a power supply which is just a 5-volt brick and a transformer in a fancy case, basically. And I still use my own power brick without any issues on my C64s. And there's devices like the C64 saver that you can put in line with your power input, so it cuts off the voltage should there be an overvoltage. There's some aftermarket power supplies that you can just buy for very reasonable money these days. I'm going to link some of the available options that I know of in the video description. If you know of any other options, please let me know in the comments, and I'm going to add them to the list. So today I'm going to build another option that was actually developed and sent to me by my longtime Patreon supporter SMD. And I have to apologize, it took me over a year to get to this, actually. I don't know, for whatever reason, it took ages. I'm sorry about that. And yeah, SMD developed several versions, actually, for replacement power supplies for the Commodore 64 and made the PCBs for them, and sent me components and PCBs in these nifty packages. So I'm going to link to this in the description as well. It's all open sourced, and you get the bill of materials and the Gerber files to make the PCBs and everything you need to make these. So that's the plan for today. I'm going to build one of these power supplies. So the messages SMD put into this were all printed on an actual dot matrix printer and are listed as basic listings, actually. So that's really cool. There are several versions of this. So as you all know, I love good documentation. This is very good documentation, available as a PDF, linked in the video description. And yeah, there's a whole bunch of explanation about why to use an aftermarket PSU and why to use this particular one, because it's higher power than most aftermarket things. There's a high power version that delivers up to 4 amps on the 5-volt line, which is plenty for anything you would ever want to do. I'm going to build the original C64 PSU replacement that delivers 3 amperes of maximum current. That's still plenty for anything you would like to do with the Commodore 64. The original power supply is rated for 1.5 amps, and that quickly gets to its limits as soon as you connect something that's a bit more power hungry, like for example the 1541 Ultimate cartridge that I use all the time, that quickly peaks higher and puts a lot of stress on the PSU. We basically have to solder all these components that are laid out on the circuit board, actually. And here's a list of how to choose the components and which components work best. And thankfully I already have all the components in here. Yeah, we have a very nice voltage regulator. That's an adjustable voltage regulator, so the voltage can be adjusted to make up for cable length losses and things like that. We have some nice tantalum capacitors and a mains filter capacitor. And here's the circuit boards. By the way, if you happen to want to make your own PCBs like these, I highly recommend checking out my sponsor for this video, which is PCBWay, a manufacturer of prototype PCBs just like these. And you can literally just take the files that are linked in the video description and upload them to PCBWay and have your PCBs for this project or other projects made. They offer high quality PCBs with very fast turnaround times, excellent service, and very reasonable pricings, so they are perfect for projects like these. This is, as I said, the adjustable version, so we have our adjustable voltage regulator, and otherwise it's pretty much similar to the linear power supply that we originally have in the Commodore 64, except it has this region here which is a C64 saver circuit, so this is an overvoltage protection that's added to this, which is, I guess it's a bit overkill because I think the voltage regulator itself has overvoltage protection already, but yeah, it doesn't hurt to have multiple protective layers here. And this works with the relay. I'm just going to solder on the components, and then we'll have a look at which transformer I'm going to use for this, because you need, of course, the Commodore 64 has 5 volts input voltage, 5 volts DC input voltage, and it also needs 9 volts AC input voltage. In the original power supply, they are derived directly from a transformer, and I think that's what this also does. So we need to solder in all the components except for R2, because R2 is the resistor that determines the shutdown voltage for the protection circuit, for the C64 saver circuit. Okay, let's put in the components. I already have heated up the soldering iron, and yeah, let's see. Oh, and the usual disclaimer applies here as well, of course. If you are not sure what you're doing, if you don't know how to solder, if you are not confident to build mains powered devices, which this is in the end, please ask someone who knows how to do it. And everything you do at your own risk. I am just doing this for myself, basically, and showing you a possibility of doing things, but I'm not responsible for anything you do. Okay, so that out of the way, let me build this. I think I want to start with the smaller parts. Yeah, let's start with the resistors, actually. Yeah, we have these terminals to attach, and then we have connection points for 2 LEDs, which are also included. Nice 5mm LEDs. Yeah, there's a lot of different options you can do, and everything's explained in great detail in the little PDF that's part of this. And there's also explanations for all the components and why they go where, and possible different components you can use. I'm just going with the ones provided here. I had to use some of my own resistors actually, but yeah, otherwise it's all as was provided by SMD, thankfully. So yeah, okay, let me put these in, which are screw terminals for the voltage in and out, I guess. And you can of course use like plugs, which would be a bit more elegant, I guess, but these are fine. In order to set the cutout voltage for the little overvoltage protection circuit, we have to determine the value of R2. And for that purpose I have hooked up my bench power supply here. That is an adjustable power supply. And we should have, ideally, a cutout voltage of somewhere between 5.2, 5.35 volts, so we don't get massive amounts of overvoltage on the output. So I've hooked up my power supply to C5, which is this tantalum capacitor in this case, and we are going to slowly raise the voltage on the power supply. I have my multimeter hooked up here as well, so we can see the voltage. That is simultaneously hooked up to the power supply and to our capacitor here, so we can monitor the voltage closely. And we should have a click in the relay between 2.5 volts and 3.5 volts. That's the moment the relay has enough power to actually close. And then we should have the cutout voltage at some point where the relay opens again, where this circuit actually starts to work. And depending on the diode you use in the circuit, you have different cutout voltages. That's basically you adjust R2 to the cutout voltage of the particular diode you're using. So we are using a XY4V7 diode in this case, and I try with the 470 ohms resistor, which I have inserted here loosely, just holding it so that the legs make contact and don't make contact with anything else, so nothing shorts out. It's a bit tricky, but yeah, I tested this and it should work. When I tested this, I saw a cutout voltage at around 5 volts. So let's see. Can you see this? Yeah, probably. So we should hear the relay click at some point here. There we go, 3 volts. And we should hear it click again at the cutout voltage. Okay, that was around 5 volts. Probably very much spot on 5 volts. So our little resistor should be another value. And according to my cheat sheet here, which already gives me values that SMD found to be accurate, we should be fine with the 390 ohms resistor. Unfortunately, SMD already provided one, so let's try that and see if that changes our cutout voltage to the desired 5.36 volts. So this was a 470 ohms resistor. Okay, let's try that again with 390 ohms in there. Okay, first click. Yeah, that's around 5.3. That's actually, that's good. So that's perfect. Let's solder this one in. Okay, so this concludes building this PCB. We of course need a transformer and we need a case and we need to connect some LEDs. I want to do that, a green and a red one actually, that display the status of this thing. So for the case, I have this thing lying around, which is a metal case. If you use a metal case, you have to connect the case part to earth, ideally. So we are going to do that in this case. Just opening it. Oh yeah. This looks pretty nice, actually. And it's red. I don't know if the color matters, but red looks nice. So we have these panels here. These are actually holding together the two halves. So we have to remove the screws to get the panels out, so we can drill the holes for our cables and things to go in. And this should technically fit our transformer. So I am going to use this plated perf board that's plated on one side, and I'm just going to cut it. I think I want to bend the pins and remove some of the plating. And we can actually add screws here, which is probably a good idea. So first thing I want to do is to put some of these screw terminals on here. So we have all the connections on this side of the perf board. And in order to remove these pads, I'm just going to remove some of the pads so we don't get our connections too close to each other. I'm just going to overheat them, and then you can actually just remove them. They're not stuck on there. This is actually using what accidentally happens to our advantage. So yeah, that's an easy way of doing this. So I'm going with the same basic principle of using component leads to make the connections and then filling up with solder. That's the same method I used on my highly discussed TRS-80 PSU. That's the plan. Let's make some nice connections here. So one side effect of this is going to be that it's going to be quite modular. So if we want another transformer, basically we can just replace the transformer. So I drilled a hole in the casing for the grounding screw. Think might have to do the same on the top part as well. So I think this is how I want this to sit in my enclosure here. By the way, the transformer is 18 VA, which is similar to watts for each output, 230 volts primary and 2 9 volts secondaries. You would have to use one that suits your particular mains voltage, of course, for your country or your place. The PDF manual details what transformers are suitable. So, and here's how I want this to sit in here. AC coming in here, like the mains AC, of course. The output AC voltages are here. and they are going to feed in here and directly out of the power supply, because 9 volts AC is one of the voltages the Commodore 64 needs. And we're going to have fuses on both outputs. I think that's what these are for. I'm also going to add a fuse on the input of the transformer and a main switch. And for putting these in here, I'm going to use my adhesive standoffs that I use all the time. For the transformer, it's probably a good idea to secure it in place with screws. These standoffs look like this. They feed into 3mm holes and then just lock into place. And they have this adhesive backing here, which it holds really well. But yeah, over time it's going to probably work itself loose. So don't use these in an environment that gets shaken a lot. And always secure stuff with another screw or some other method. So these should fit perfectly into these holes. Do they actually? Yes, they do. So, and as you can see, I have cleared out all the pads around the conductors. So we're going to be fine with this thing, I guess. Yeah, this is so not going anywhere anytime soon. Yeah, I think I might want to drill some holes for this transformer. Here's a nice tool I came across recently. This is a marker that has a carpenter pen that has a long shaft, so you can mark things to drill through things. Which is actually really useful for a lot of things. Can recommend getting one of these. So I think it's time to start with designing the panel, the side of this where our mains comes in. And I want to fuse the mains, so I got another fuse holder. These are the ones for the outputs that are going on this side. And on this side I just want a fuse and the cable coming in, the mains cable, I think. So I have the main switch and the fuses and the LEDs on the other side. It's probably a good idea. For my cable, I'm just going to use this leftover, I think, PC cable probably. It's one of these IEC 3-prong connectors. And yeah, you need one for your particular kind of main socket, of course. This is a rather beefy one, I don't know. It's a bit overkill for this. I'm going to use a little rubber grommet to feed it through and secure it from the other side. Usually I can get away with that. You can use 2-prong cables as well, but I'm using one that has the PE, so we can connect the metal case. If you have a plastic case, you don't necessarily need a 3-conductor cable. Yeah, I think I need to widen this a bit because the cable is wider than I anticipated, and I still want to fit a rubber grommet, something like this, in there, and then secure it from the other side with some cable ties, I think, and it's going to be fine because this is going to be quite stationary for my Commodore setup. By the way, these step drills are one of the best inventions ever. So far I have my live wire coming in here, going through the fuse, and then ending in this, which is going to go to the mains switch, which is going to be on the other panel. And I have my PE, protective earth, that I'm going to crimp this little ring connector on. If it fits, hopefully. Yeah, it does. And that is going to be affixed to the case. And I think, yeah, probably there's going to be another wire coming from the case, going to the top half of the case, and also being screwed to the case. So we have a secure connection there. So it's time to lay out this panel that's going to be on this side, which is going to have the on-off switch, which is a mains power switch, 2 LEDs for the status of the C64 saver, 2 fuses for the 9 volts AC and the 5 volts DC, and we are going to have the cable supplying the Commodore 64 coming out here. I actually decided this layout with the kid yesterday, so we had a bit of a philosophical conversation about this interface design, which is, yeah, it is kind of interface design because it is the side that interfaces with the end user of this, which is going to be me mostly, probably, but that's all right. So yeah, I'm going to try to mark this and have it lined up nicely. And then it's going to be time to drill some holes. So I think that turned out rather nicely, and I guess everything should fit. For the cable, I'm using this 4-wire lamp cable again. So we have 2 wires for the AC and 2 for the DC. And yeah, we don't want to go that long, like maybe 70 centimeters or a bit more, maybe. That's great. So now here's the problem we have with this wire that I've faced numerous times whenever I use this. And I am going to face it again in the comments section, I'm sure, because this yellow and green wire should be PE. This should be the protective earth, no matter what. And because this lamp wire is made for mains connections, this is meant to be PE in that case. We are not going to use it for PE. I am, however, going to use it for the ground connection for the 5 volts DC, so it's the closest to PE we have coming out of this power supply. It is floating ground actually, because our PE from the mains is only connected to the case, just like in the original, power supply they don't have an earth connection at all. So we have a floating ground, just like in the original power supply the Commodore 64s come with. I hope you understand. This is something you shouldn't do for a production kind of thing. This is for my private use, so I am going to get away with it, just so you know. So we want green, yellow, ground. We want, I think the brown and the blue should be our AC, and the black one, even if it's kind of odd, should be our 5 volts. And we need to go through each of these fuses. The 9 volts AC, one of the phases goes through one fuse, and 5 volts goes through the other fuse. Yeah, the other phase of the 9 volt AC comes directly from the transformer, and the ground should come from our ground socket on our little circuit board. First I want to connect the power switch, and this is a model that connects 2 phases, so we are going to switch the live and the neutral, which makes sense for countries like here in Germany, where you don't have polarity marked in the outlets. So live can be neutral and neutral can be live, so you should wire things up so that the live wire is disconnected in any case. So we are going to go, these are our mains connections, the live wire going through the fuse, which can be live or neutral. You could of course put fuses on both phases as well, but I think that's a bit of overkill. Not that this thing wouldn't be overkill. It is kind of overkill in many aspects, but yeah, it is what it is, and everything that's worth doing is worth overdoing, I guess. So let's connect these to the power switch here. And I'm using crimp connections, I think, for this purpose, and heat shrink tubing as well. So, and after our inlet of both phases to the switch, we are going to feed the switched pins to the input of the transformer. So for the status LEDs I'm using smaller wires, of course, and yeah, I have not clipped this in yet because there's some things to consider still. And I'm using black for the negatives and red and green for the positives, I think, so we don't get things confused. The resistors for the LEDs are already present on the board. And I drilled 5mm holes for the LEDs, so they are going to fit through these holes, and I'm just going to keep them in there with some glue later. So yeah, I think we only have to connect our 9 volts AC from one side of the transformer to our little PCB here, and we're ready to test this. Oh, and obviously we have to connect the other end too. So our AC input, 230 volts from the power switch. By the way, those of you who commented on the last power supply build video, or these clamps are actually made for stranded wire and for solid wire, so I don't have any worries there. People said you should have solid wires for these. We're going to be fine there. Oh, and I'm also going to add a heatsink to the top of the bridge rectifier, which gets rather warm actually. So I'm adding a heatsink on top of this for good measure, and so that it runs as cool as possible, which is also always desired. I think we have everything connected actually. Oh, for the fuse on this end actually, let me show you how to determine, or how I determined the size of fuse I used. So I'm not the best at math, but we have a 36 watts transformer, so that's going to be the maximum power we use. Power equals voltage times current. So we want to know current. So we have to divide by U or V, depending on where you are, and that's our I. So we know our power, which is 36 watts. We know our U, which in my case, because I'm in Germany, is 230 volts. 36 divided by 230, that's 0.156. 0.156 amps actually. So I don't have many fuses, but I have this 315 milliamp fuse. That's about the closest I can get to this. You can go slightly higher than this, and you should use a slow blow fuse where there's a T. So this is a slow blow 315 milliamps fuse, which is around double that. So on the other side, both our AC output and our DC output are fused with 1.6 amps each, which is around the highest output rating this is going to get. So let's see if this thing actually blows up at this point or if it works. Plugging in. Didn't say anything yet, so that's a good sign. Let's turn it on. And we have a green light. Yeah, things should be alright on the output side. Let's measure the actual output voltages. One last thing that's worth mentioning is that R8, the little resistor you can see down here, I've populated that with a 2.7 ohms resistor, 2.7 kilo ohms resistor as specified on the PCB. This is actually the resistor that sets the output voltage for the little regulator. You can use a lower resistance to slightly increase the output voltage to make up for cable losses, but I have a really short, really huge diameter cable here, so I'm just going to see how much we get on this end of the cable and if it's actually necessary to replace that resistor. SMD recommends to use a 2.53K resistor made up of one 2.2K and one 330 ohms resistor, so I haven't clipped this in completely yet, so we are going to see if that's the way to go, or if we can get away with just using 2.7K. At this point we should probably feed the housing for a connector over the cable, which I otherwise tend to forget. This is a Hirschmann brand one, which I really like those, and it's an MAS 70S. That's the kind of connector. It's a 7-pin DIN round, like in a circle, not like the horseshoe connector. So that's the one you need. And yeah, these Hirschmann are very good quality. And this is going to work very well. But I tend to forget to slip this housing over the cables. So, alright, let's plug this in again. Okay, this should be our AC. And it's... oh, that's pretty good actually. That should be spot on 9 volts, a bit higher because it's there's no load. This is 10 volts, that's perfect actually. So under load it's going to be roughly 9 volts, which is very nice. And here's our DC side, which indeed is a bit low after the losses in the cable, and under load it's going to be a bit lower still. So we are going to put the 2.53K resistor in there, I guess, which should give us 5.2 volts at the output of the regulator there. And yeah, we are going to put these in there. So now with the new resistor in place, the 2.53 kilo ohms, we get 5.18 without a load, which should drop down by 0.1 volts with a load or thereabouts. So depending on the load, of course, it's going to slowly drop. So this is going to be perfect for powering a C64. So time for connecting the plug. This is, as I said, 7-pin DIN plug. This view is from the solder side, or the socket, the actual connector on the C64. So yeah, we are going to solder our wires like so. And we only need to connect pin 2 for ground, which is the bottom middle, and pin 5 is 5 volts, and pin 7 and 6 are the AC pins. And I'm going to try kind of a new method. I'm trying to crimp on, because these wires are too thick to actually fit these little holes in the pins. I'm trying to crimp on these pin header plugs, actually, pins. So yeah, I don't know if this is going to work, but it was suggested to me by somebody. I don't remember who it was, I'm sorry. But yeah, we're crimping these and soldering these pins onto here. Maybe that makes sense. They fit the holes perfectly. I'm going to cut them a bit so they fit closer. And then I'm going to solder, and that should allow us to have a larger diameter wire in there. So that actually worked rather nicely. So I'm now going to clip these a bit so that they are going to fit fully into our hollow pins. Need some heat shrink. So now I should be able to just connect the pins accordingly. Yeah, that works really well actually. It's a bit fiddly to get it in there. But the connection is great, actually. That's actually really easy to handle. And I think it should make a pretty nice connection. And we can slide heat shrink tubing over there without any issues. Yeah, some small issues because it already shrunk. Yeah, but other than that, this is really cool. This works really easily. Nice. Okay, there we go. This should be our power plug. So obviously I want to check this again before connecting it to a Commodore 64. And here's another little trick. You can use pieces of heat shrink tubing if you want to measure in a small connector like this to not short out anything accidentally. Yep, and that's 10.44. That's nice. And now for the DC part. So if that's not a useful trick, I don't know what is. If you learn anything from this video, probably this. So that's 5.18. That's super cool. Okay, so this should technically power a C64 now. So the last thing before I close this is going to be connecting this ground lug. Okay, that should be enough. Obviously no good Jan Beta project is finished without a bit of hot glue. I'm just going to add some to affix the LEDs here. And I'm also going to add some to the power switch. So and here's the moment we've all been waiting for, more or less. Using a C64 test board. This one was donated by Bart. It's actually a working board. He didn't really know if this was working, but thank you for donating this. This is a great device for testing. And yeah, I'm going to hook up my monitor here and try if this thing actually powers the C64 and measure the voltages that come from the C64, so we have the voltages that arrive at the machine. Okay, let's try this. Turning this thing on. Oh, and this C64 was turned on actually. So now we are powering an actual real-life Commodore 64, or at least a Commodore 64 PCB. Nice. So this seems to work. So this particular machine doesn't have a SID, but we should have our output voltages here on the user port. This should be our 5 volts, I think. And it's spot on. Yeah, it was 5 for a second there, and now it's 4.99. That's absolutely amazing. Okay. And this should be our AC. which should be, yeah, it's about the same we had directly from the transformer on the cable there. Because there's very little load on the 9-volt rail, I think, especially since there is no SID in here. I think what I want to do is to connect a fully equipped Commodore 64 and see how well it works, and then also see how warm our power supply gets, and just test it for a while, which is kind of the fun part of this whole endeavor. So I'm just going to run the Cauldron demo that I often use for testing things because it's looping. And this Commodore 64 has the 1541 Ultimate 2 Plus inserted there. So that should draw a reasonable amount of current. Otherwise, this is unmodded, has an original newer generation SID chip in there. Everything's original, basically. And let's just leave this running for some time and see how warm our power supply gets. I think it should hold up very nicely, actually. This demo actually rocks quite a bit. So here we are after half an hour, pretty much under the most load that this is ever going to see used by me. And the outside of the case, I can definitely feel it's a tiny bit warm, but absolutely not significantly warm in any way. So it's not boiling. I measured the voltage on the user port again, and it's around 4.9, so it drops a bit of voltage again. But 4.9, as long as it's above 4.75, which is the absolute minimum, it's gonna be fine. 4.9 is absolutely fine. It just dropped another 0.1 volts approximately, because it's under quite some stress because of the 1541 Ultimate 2 Plus that draws quite some current. I actually want to open this up and see how warm the parts get. So here it is after half an hour under full load. And yeah, the bridge rectifier should be the part that gets the warmest. Oh, we got something like 38 there. The transformer stays cool. This is, we have room temperature, so the room is at 20 degrees Celsius, I guess. Yeah, around 20. It's perfectly room temperature. And there's nothing that's significantly warm. I think the warmest at this point is 36 degrees. So let's say with the time that it took to open this up, the highest we got was 40 degrees Celsius, which is absolutely fine for everything. And yeah, I guess my little ventilation holes that this case has are sufficient to keep this as cool as it's supposed to be. So it seems we have a slight problem in that the C64 saver circuit just engaged after more than 30 minutes. So yeah, obviously this gets too warm. This is a problem that SMD describes in the manual as well. So I'm probably going to have to set the cutout voltage for the C64 saver a bit higher. And I think this is going to work fine again after it cools off for a while. But for now, the circuit is triggered. So I'm probably going to put in a slightly smaller resistor in the R2 position to have my cutout voltage be a bit higher. And then this should probably work fine. Okay, so this is not the most beautiful operation, but I actually managed to get a 330 ohms resistor in there, so this should give me significantly more headroom for the cutout. It has nothing to do with the actual output voltage, it's just the clamping circuit drifting slightly. The transistors and like the diodes, everything changes a bit with heat. So when this gets warm, the characteristics change and the cutout voltage changes. And yeah, that is causing the effect we just saw. So probably we should actually measure this while it's warm. And yeah, we didn't do that obviously, so I'm just making up for that with a slightly smaller resistor, hopefully. Yeah, obviously it's time for another round of stress testing. It does still work, but I'm going to leave this running for an hour or so and make sure it doesn't cut out again and see how warm it gets after that period of time. So yeah, I'm just going to leave this running for now and I'll be right back. Okay, so it didn't cut out so far. Let's check the temperature. Yeah, 41. It's like, as I said, it's around 40 degrees C maximum, which is absolutely nothing to worry about for any electrical component, I think. Yeah. And this is loaded with more than a regular C64 because of the cartridge. So yeah, and I didn't have any thermal issues with my C64 saver. Let's see what happens if I turn off the Commodore 64. It cut out last time if I did that because of the sudden voltage spike. Let's see what happens. Yeah, and it actually works. So that's how it's supposed to be. We obviously have a slightly higher cutout voltage now, but yeah, this works stable now, which is worth it. And you can hear the relay clicking. When I turn it off, it takes a second or so until the relay power gets shut off and the relay clicks. Yeah, very nice. As you can see, I got some help testing this further from the kit. And as far as we can see, this is the very good replacement power supply for the Commodore 64. If you have any suggestions or ideas on how to improve on this design, please feel free to leave comments and suggestions and also links to other projects like this. Thanks again to SMD for designing this thing and for providing the parts to actually build one and for making the files for it public. And yeah, the links are in the description. Thanks to everybody who supports me. Thanks for subscribing to my channel. I'm Jan Beta. Thanks for watching. See you next time. Bye.